This video explains and derives relationship for linear magnification of spherical mirrors. Linear magnification is defined as the ratio of height of image to that of the object. It is denoted by m and equals h2 over h1, where h2 is the height of image and h1 is the height of object. Let's now derive a relation for m in terms of u and v, where u represents distance of object from pole, whereas v represents the distance of image from the pole. Let's first see the case of concave mirror. Consider a concave mirror with pole P, focus F and center of curvature C. An object AB is placed beyond C. The light ray parallel to the principal axis passes through the focus F. The light ray through the center of curvature C retraces its path after reflection, and the ray at the pole reflects according to the laws of reflection. All these rays meet at a point to form an inverted image denoted by A', B'. According to the sign conventions, the height of the object AB equals positive h, while the height of the image A', B' equals minus h2, since image is formed below the principal axis. The object distance equals minus u, since it lies left to the pole, and the image distance equals minus p for the same reason. Since triangles ABP and triangle A'B'P are similar, therefore the ratio of their corresponding sides are proportional. So, ratio of A', B' to AB equals ratio of PB' to PB. Putting the corresponding values, we get minus h2 over h1 equals minus v over minus u. On simplification, we have minus h2 over h1 equals v over u. Since h2 over h1 equals m, therefore m equals minus v over u. For the case of convex mirror, consider a convex mirror with pole P, focus F and center of curvature at C. Object AB is placed in front of the mirror. A ray passing parallel to principal axis diverges and appears to be coming from the focus. The ray incident on center of curvature reflects back along the same path. The ray incident on pole diverges in accordance with the laws of reflection. When reproduced backwards, these rays appear to meet behind the mirror. The virtual and erect image is formed at A', B'. Now, according to the sign conventions, the height of the object AB is positive h1, the height of the image A', B' is positive h2, as both are above the principal axis. The distance of object PB equals minus u, as it lies left to the pole. The distance of image PB' equals positive v. Now consider triangle ABP and triangle A'B'P. As the triangles are similar, therefore ratio of A', B' to AB equals ratio of PB' to PB. Putting the values, we get h2 over h1 equals v over minus u. Since h2 over h1 equals m, therefore m equals minus v over u, which is the required relation. Since linear magnification is same for both the mirrors, we can derive magnification in terms of u and f, where u represents the distance of object and f represents focal length. As mirror formula equals 1 upon f equals 1 upon v plus 1 upon u, multiplying this equation by u, we get u over f equals u over v plus 1. On transposing, we have minus u over v equals 1 minus u over f. Taking LCM, we have minus u over v equals f minus u over f. On taking reciprocal both sides, we get minus v over u equals f over f minus u. Since magnification equals minus v over u, therefore m equals f over f minus u. To obtain the relation in terms of v and f, that is distance of image from the pole and focal length, multiply the equation of mirror formula by v throughout, we get v over f equals 1 plus v over u. On transposing, we have minus v over u equals 1 minus v over f. Taking LCM, we get minus v over u equals f minus v over f. As minus v over u equals m, therefore we have m equals f minus v over f, which is the required relation. So this was it for the video. See you in the next one. Thank you for watching.